no. Sí.
Está el botoncito encendido. Bueno, vamos a empezar. Me alegro ver que hay muchas caras conocidas, pero por vez primera los veo aquí. Así que bienvenidos a todos. Hoy de forma excepcional le he pedido a Luismi que me ceda la palabra para presentar al conferenciante de esta sesión, Rubén Laplaza. Como sabéis, Rubén ha obtenido recientemente una plaza de investigador científico y está a la espera de tomar posesión para incorporarse a nuestro instituto. Rubén es especialista en inteligencia artificial y su incorporación responde a una apuesta de la dirección para impulsar la integración de la inteligencia artificial en la línea de investigación de todos los grupos de este instituto. Todos sabemos que los indicadores actuales apuntan a que la inteligencia artificial va a ser una herramienta clave en la ciencia del presente y del futuro. Y no podemos quedarnos atrás. De hecho, en la evaluación del proyecto científico DeepMax del Instituto, en el apartado de actuaciones para fortalecer el liderazgo científico y transversalidad tecnológica, se hace una recomendación muy clara: redirigir todos los recursos hacia áreas emergentes como la computación avanzada y la inteligencia artificial para mantenernos competitivos. Bueno, esperamos todos que la llegada de Rubén nos ayude precisamente en este sentido. Ahora voy a decir unas palabras muy breves sobre el currículum de Rubén que me ha pasado. Rubén se graduó en química en la Universidad de Zaragoza, donde ya empezó a interesarse en la química teórica y computacional, especialmente en el estudio de las interacciones fármaco-proteína. Después cursó un máster de química teórica y modelización computacional en un programa conjunto entre la Universidad de Santiago de Compostela y la Universidad Autónoma de Madrid, obteniendo el premio extraordinario del programa. En el 2020 se doctoró en química teórica en la prestigiosa Universidad de la Sorbona en París, bajo la supervisión de los profesores Polo y Contreras García, centrando su investigación en la teoría funcional de la densidad y el estudio del enlace químico. Después ha trabajado como investigador principal en otra institución prestigiosa, como la École Polytechnique de Lausanne, en Suiza, y ahí trabajó bajo la dirección de la profesora Clémence Corminbeu. En este verano, Rubén, dentro de poco, Rubén empezará su carrera independiente con nosotros. Bueno, Rubén, bienvenido al instituto y estamos todos esperando escuchar tu charla que has titulado Quantum Chemistry, Software and Data, a Joint Venture Towards Inverse Molecular Design. Debo de admitir que la mitad de las cosas no le he cogido, así que espero enterarme.
Eso vamos a intentar, Vale. ¿Preferís que haga la charla en castellano o en inglés?
As you want.
Sin compromiso. Ok. Quizá lo hago en inglés por mantener el título, por mantener la fidelidad del título. So, well, thank you, Nureddin. I'm very happy to be here. It's a pleasure to meet you all for maybe the first time for most of you. And I'm going to try to present this sort of generic overview that has this complicated title, Quantum Chemistry, Software and Data, because my goal here is not so much to show things that I have done in the past, but rather to show things that can be done in the future. Because as Nureddin said, and I honestly believe this is true, my goal is to try and find common things that we could work on together in my future here, which I'm very excited for. And I guess that in general, since the application of artificial intelligence in chemistry is relatively new, many of you would not necessarily be familiar with the stuff, with the aspects that we could bring to the table. So, before I start, I'm going to thank and acknowledge that the stuff that I'm going to be presenting on is the work of many people. This is mostly work that I've done during my 5 years as a postdoctoral researcher in the group of Professor Comminbeuf, in which I had great associates to work with within the group, and also great students that I mentored or supervised, either bachelor's or master's or PhD students, as well as excellent collaborators such as the group of Markus Reyer, Nikolai Kramer, etc., both in EPFL and in ETH. Now, as Nureddin said, I am, in a way, a quantum chemist by trade, right? My PhD was in quantum chemistry, and that's what I sort of grew up doing, academically speaking. And in quantum chemistry, whenever we do computations to either help experiments or on our own, we basically get a molecule or a material, and we try to compute its properties using equations, such as the Born-Oppenheimer equation, right? That govern the movement of electrons and the properties of electrons, right? And this is very useful, of course, because we can then rationalize and predict the properties of new materials without having to go to the wet lab. We can therefore guide experimental efforts without having to do trial and error. We can try and derive the sign principles. What happens if I put a new methyl group here? And then I switched into more machine learning aspects. And in machine learning, generally speaking, what we do is we take a molecule or a system or an experiment even, and we write it as a representation, which is basically something that the computer can understand, right? And this representation is then fed to data-driven algorithm. This is what we call the model typically, and the model allows us to obtain maybe in some aspects the same things that the quantum computations would allow us to get, such as the properties of the system, the outcome of an experiment, well, the things that we are interested in anyway, right? However, to make this sort of switch is not always trivial, of course. Otherwise, everyone would be doing it exclusively, because quantum chemistry is deterministic. It's based on first principles. We solve some equations. We know the equations. They are hard to solve, but we can just deal with them. Whereas in machine learning, or in the application of machine learning to chemistry, of course, we have to deal with data availability. Do we have enough data so that we can teach our model to predict on new data? Are we confident that we can make predictions on molecules that are different from the stuff that the model has seen in its training process? Are the models or the algorithms easy enough to use? Are these things that the users that are going to be using it for making predictions are already familiar with? And of course, the explainability aspect, right? We have a model, it can give us a property for a molecule, it can give us the outcome of a reaction as a prediction, but do we know why the model is going to predict what it's predicting? And all of these things basically require a complete infrastructure. And I will continue explaining a bit what I mean by this. So, for instance, in my group, we've been working for many years in predicting molecular fields using machine learning, such as the electrostatic potential, so we can get the electrostatic potential of a protein to understand the binding pockets. We can predict the electrostatic potential of a molecule to see which side will be more reactive. And we have trained models to do this without having to do the quantum chemical computations or the DFT that would let us do it. But this was, of course, the effort of many, many years with many different moving parts, and not all of them are so to say, exciting from the scientific point of view. Because, well, ultimately what we typically want to do is go from a target property, right, to the optimal system. And this is not only property prediction. Say, maybe I can make a prediction of what the property will be for a molecule. For instance, I can try to predict the yield that I will get from a catalyst, right? But this is not enough, right? We want to predict, ideally, what is the best catalyst to obtain the best yield for a given transformation. And that is very difficult. Because indeed, to do that, you will need to deal with data sets, right? You will need data to train your machine learning models. Maybe this data is not available. You will need maybe to develop new concepts. You will maybe need software. You will maybe need to define what are the properties of interest. Because, of course, sometimes things in chemistry are not only one dimension. Say, maybe you want a catalyst that is very good in terms of yield, but you also don't want your catalyst to cost $2 billion because it's made with particular isotopes of uranium, of course. So all of these factors have to be taken into account. And this means that we need to build a lot of different components that only after these are built, we can assemble together to truly do, or to truly attempt to do, inverse molecular design, to find the system that we really want to satisfy our properties of interest. And this is sort of what I've been trying to do. During my postdoctoral years, I mostly worked as to develop a platform that we call Navicat, because it was mostly dedicated to catalysis, in which we try to sort of try and build all these independent components and then showcase how we can put them together to do truly inverse molecular design. Now, as part of this, I work in many different areas, right? So I work in things such as developing volcano plots. Volcano plots are basically something that is very known in the heterogeneous catalysis community. So we try to predict what is the optimal sort of catalyst for a transformation. I work in things such as genetic algorithms that I will talk about later to try and find, by using basically the techniques that evolution uses, what is the best catalyst for a transformation. I've worked in microkinetic modeling to try and build models that can bridge between experiment and theory. And all of these things I've always tried to build, not only thinking about my own use, but also as tools that can be used by the community. That is, we, and me in particular, have always been trying to make these tools fully open source, publicly available, community-based, and shareable. In fact, all of these things that I'm going to be talking about are things that can be fully accessed through either GitHub or DOI-identified repositories following the FAIR principles. And indeed, even though we have many such tools, all of these tools then, which are mostly software, can be connected with one another to do more complicated things, as I will show later. Now, a very critical aspect of any machine learning effort is data. And I would just like to spend maybe 1 minute to highlight the importance of molecular databases and the importance that this field is going to have in the near future. So one thing that I've been working on actively as a part of this Navicat project is in developing databases that can then be used for machine learning efforts. For instance, and without going into much detail, we have worked a lot in building databases of organic molecules for organic electronic applications. I will talk about this a bit later. But we've also been working in developing databases of organocatalysts. We have a database of millions of organocatalysts that we take by either looking at the literature, looking at everything that has been done experimentally, looking at crystallographic repositories, then putting things together. We've also worked in mining transition metal complexes by mostly screening the CSD. We've also built increasing numbers of databases for ligands so that we can have all of these collections, not only for our own use, but also publicly available in a way that other people that are working in data-driven sort of applications can profit from them. Particularly, we've also built this cell-to-more tool. This is mostly the work of the PhD of Yuri, and also with collaborators. And we built a tool that can read ZIP files from crystallographic repositories, but also the ZIP files you obtain directly. And it can process them into independent molecules, so it can identify all the molecules that form your molecular crystal, and then recognizes sort of the graphs and the compositions of each of these molecules, assigns what is the charge, and that also means the oxidation state of the transition metals apparent, and also tries to assign what is the most likely spin state for all the metal centers. And while this seems like very boring, it is extremely important, because only by doing this, then we can have a database that can be used in machine learning applications. And we also built a user portal that you can go in your browser and you can upload your ZIP file and get the information downloaded in a way that can be used for machine learning applications. So this is just to give an example of the things that sort of sound boring that sometimes you have to do, so that then later you can find a database of, I don't know, copper, pincer, or any area of chemistry that you're interested on. Because otherwise, if I tell you, find me all the sort of pincer ligands that you are interested on, you would have to go to a web portal by a company and try to find all the appearances of a given substructure. But then if I want more information about them, such as I want only the pincer ligands that have been found between this year and this year in coordination with this particular metal, in this particular oxidation state, in this particular spin state, that would be far too much. So sometimes you just have to do the data engineering part and get the data in a way that can be used later on. Now, sorry, the other way. Well, this is just an example of what this cell-to-more thing does for you, for instance. And this is being quite popular. I think a lot of people are using it nowadays to process, just to process ZIP files. Now, just as a brief look, I commented on that we have a database devoted to organic electronic applications. Now, I know that organic electronics is not maybe the most exciting field for this institute. Now, I assure you that most of the things that I'm going to comment on, we've also done for catalysts. And the only reason I've chosen organic electronics, or let's say small organic molecules as a field to demonstrate today, is because we've really done everything that can be done on this area. And I just think it will be interesting to show the chronology of how, over the years, we've done more and more complicated machine learning approaches to a particular organic electronic application. Okay? So what we did originally, we took basically every organic molecule with P block elements in the CSD, extracted them, categorized them, obtained their geometries, and performed TDDFT computations to obtain the excited state properties for all of these molecules. And this means we have now the singlet and triplet energies of all of the organic molecules that have, I cannot promise 100%, but most of the organic molecules that have ever been synthesized and deposited in a crystal structure. Okay? And then we can plot the singlet and triplet energies, and it turns out that the singlet and triplet energies in organic electronic applications is a lot of what you care about, right? A lot of the applications that we see in LEDs or in solar panels deal with what is the sort of excitation on the singlet and the excitation on the triplet. And in particular, this let us see also what is the general spread of this property in most of the molecules that have been synthesized. And this is relevant because then we can build machine learning models, in this case based on this database of over 100,000 molecules. And now we can have a machine learning model that can predict the excited state properties for almost any organic molecule that one would be interested on. And now this can be used for organic chemistry, for general organic chemistry, can be used for photosensitizers, can be used for organic electronics, as I will demonstrate later. And then we can also analyze trends. We can look at what are the things that contribute to a higher singlet. We can look at the things that contribute to a higher triplet. We can understand why the models are making predictions. We can even try and see what are the things that make the model have more error to try and understand how the models are working. And all of these things are important diagnostics. For instance, again, not going into much detail, but you can see here that we can sort of see the error depending on the substructures, that is the functional groups that are apparent in molecules. And we can see, for instance, that our models are pretty good, but they give us much higher errors when we try to predict things such as molecules containing selenoketones, right? And this makes perfect sense because selenoketones are not a very common functional group, and therefore, if we take a database of molecules in the CSD, we will have very few examples with selenoketone functional groups, and therefore our models will not be able to make good predictions on the excited state energies of selenoketone containing groups. And this is important because we need to know these things so we can then know what our models can and cannot do, right? So now, we have all of these things, and that means we can now look into applications, right? Let's try and find new molecules with properties of interest now that we have machine learning models that can cover those. So, molecular design strategies that can be attempted through machine learning, grosso modo, can be divided in 3 different ways, right? So the first thing that you can do is, well, you start from a chemical structure database, right? And then you do high throughput screening, or virtual or in silico high throughput screening, right? Why we can do this? Because now we have machine learning models, which means that we can compute the excitation energies of these molecules in few seconds. The same could be said if we were applying this to catalysis. We could have a database of catalysts, we can have machine learning models to predict the yield or the selectivity, and now we can screen any database that you want in a few hours and look at what the results do. And this is of course convenient because it's pretty straightforward. You just need models that work. But it has comparatively high cost and low heat rate. And what do I mean by this? Well, what I mean is that even if you have a machine learning model that can predict the properties of interest in, say, a second, and it may seem that a second compared to a full experiment is extremely good, if you have to cover 10 to the power of 60 molecules because you're trying to cover any possible molecule in existence, a second would still mean that you would have to wait until the universe dies and we would turn into iron. So this is obviously not the way to go for every application. Now, instead of doing that, you could go a bit smarter. You could do something fragment-based, such as genetic algorithms. So what you do basically here is, instead of trying to predict on every possible molecule, you chop your molecules into little pieces, such as functional groups, or say maybe you have don't know, a pincer ligand, and you decide, instead of exploring any possible molecule, I'm going to only look at these central units and these side units, or maybe you have a carbene and you decide, okay, I'm going to look at this central part and I'm just going to change the different substituents. And this, of course, is much more efficient than trying everything. So you get some sort of an efficient exploration, but the bad part is that whenever you have fragments, you have some heuristics in the sense that you have to decide what are the parts that you are going to cut and put together. And maybe you think that you are being very smart because you are only checking the substituents that go into an N-heterocyclic carbene central core, but by doing that, you are not trying something else, such as modifying the central part of your carbene, and actually the best possible ligand would be the one that changes the central part of the carbene, right? So heuristics are good because it lets you, reduce the number of molecules you have to screen, but maybe you pay a price for it. So you never know. So then there's a third option, which is maybe the most fancy one, which is to go to full-on generative models. So in essence, what the generative models do is you take a machine learning model, you show it a lot of molecules, and you teach it to learn the structure or the composition of these molecules, and then you ask it to generate new molecules by, more or less following the rules of what it has observed. So more or less what, ChatGPT does for language, right? We take ChatGPT, we teach it a lot of language, it learns how to predict the next word because it has seen the probability distribution of words. We can do the same on chemical structures. We can train the generative models that produce new molecules based on some distribution of observed molecules. So this is bias-free in the sense that we are not imposing some sort of heuristic rules to cut the molecules into pieces, but there are, since this is very new, a lot of questions regarding what kind of exploration or what kind of relevance these new molecules are. In the sense that, okay, very cool, we have this machine learning model, but maybe this machine learning model, it will only produce molecules that look very similar to the most common molecules in the training set, right? So not that interesting. Or maybe the molecules that would be generated by these machine learning models that are trained to be generative will be completely irrelevant because they are molecules that cannot exist, they don't make sense, they cannot be made in the laboratory. So a lot of questions in that regard. And luckily, we've sort of applied all three to the design of singlet fission chromophores. So this is the boring part in the sense that I know that organic electronics is not the bread and butter of the institute, but I think it's cool because then I can show you how these different approaches have led us to different results over the last few years. Okay? So without boring you too much, in singlet fission, which is interesting because this has applications in solar panel devices, you ideally want to find an organic dye or an organic molecule that follows these energetic criteria. Well, the main application of it would be that you want a molecule that can absorb a photon from the sun light of the sun, and then this singlet excitation can be then divided into two triplet excitations, because if you could do this, then in solar panels, everyone would be very happy because from one photon you can generate two photons, and that means that your efficiency as a solar panel increases a lot, and we can build better solar panels, and we can deal with climate change. So, of course, this is very interesting for a lot of people. And for that, you need organic molecules that fulfill these energetic criteria. You need that the energy of the singlet excitation is at least twice the energy of the triplet, because if you need to produce two triplets from one singlet, you need thermodynamics to be like that. You need that the energy of the singlet is at least lower than 3.8 electron volts, because otherwise your molecule will not absorb any energy from the sun. And you need that the energy of your triplet will be higher than 1.10 electron volts, because otherwise the triplets are useless. You need to put the triplets into silicon to then make electricity. So again, this is just an example of an application in which we want to find organic molecules with a very constrained set of properties of interest. You can imagine that this sort of problem is basically everywhere in chemistry. Same as trying to find a catalyst that fulfills a given set of properties. Say you would want the yield and the energy selectivity to be both within some range. But this is the case that we've been working on with all these three families, and this is the example I'm going to stick to. So, as I said, we focused on this problem originally by using this foam database, because we have this database of organic molecules with all of their excited state properties. And then the first things we did were try to do high throughput screening and try to do genetic optimization. So, just to show you the examples, we looked at the distribution of these properties in form, and we found that indeed only a relatively small amount of molecules are in this corner here. This corner here is the one that satisfies the criteria for singlet fission in terms of singlet and triplets. It's a bit hard to see because there are 100,000 points in this image, but the number of points here is very, very small compared to the number of points in the main sort of line. And luckily, let's say, we were satisfied because we could see that in this corner here, indeed, we find the molecules that are experimentally known to have potential for singlet fission, which are typically either body pies or acene molecules like pentacene, anthracene, molecules with a lot of fused aromatic polycyclic moieties. Now, starting from there, the first thing we did, take form. We have our database of organic electronic molecules. Let's put them together. So we took molecules from form, and we found CSP2 carbon sites in all of these molecules. And then we built new molecules based on form by doing this cross-coupling, because we thought that this cross-coupling operation would sort of be synthetically relevant in the sense that it's a typical reaction that can be performed. And by doing this, we can put together, from our original database of 100,000 molecules, 149 billion possible dimers. By dimers, I mean molecules that would be originated by doing cross-coupling of our original database, which is molecules that we know have been synthesized and crystallized. So, in principle, we now have 149 possible organic molecules that should not be too crazy to make. And then we can scan those 149 molecules using our machine learning models, right? And then by doing that, we find a new distribution, and we find some new molecules in the area of interest with properties that are interesting to us. Most of them, as you will see here, have some sort of strange, highly charged sweeter ionic rings that nonetheless are found in molecules that have been synthesized and crystallized in the CSD. So, well, we were pleased so far that we have found combinations beyond the original database and molecules or combinations of molecules that nobody had looked at, but let's say we were not entirely satisfied by the results so far. And then, of course, we realized that even with machine learning, once you start putting new molecules together, you quickly go to billions and trillions and so on, and even when computing the properties only takes a few seconds, there are limits to what we can do. So, as a natural continuation, we went into fragment-based strategies, right? So then we went into genetic optimization. So we cut our original database into cores and substituents, and then we defined rules to put together the cores and substituents. So basically we define cores. We define cores as CSP2-based conjugated systems, and then substituents as anything alkylic that you can put in the combinations, right? And then by doing this, we can create a sort of search space of possible molecules that in here is of the order of magnitude of 10 to the 12 molecules. So there are many, many molecules. And then we can use a genetic algorithm using different machine learning models to predict the properties of these sort of molecules, but not in a high throughput manner. That is, we cannot cover 10 to the power of 12 molecules because then that would take far too much time. So what we do is we use a genetic algorithm that for any possible combination of the fragments evaluates what are the possible properties of this molecule, plus minus the uncertainty of the machine learning model, and then we iteratively drive this sort of genetic algorithm towards molecules with higher potential, but that means maybe the machine learning models are being very extrapolative and they are making a mistake, or we can choose to go to predictions in which the machine learning model has very little risk because there is very little uncertainty, but of course that also means that the chemistry will be less interesting. And indeed what we see is that if we allow the machine learning models to be more uncertain, that is, we are explorative in nature, we can find new molecules that nobody had explored for single feature application. But if we are conservative, that is, we don't want any uncertainty in our machine learning models, we want our machine learning models to just give us the best possible numbers, then we mostly rediscover known single fission materials that have already been studied and discarded for other reasons. So what I mean to say by this is that, as I commented on before, the domain of applicability of your machine learning model is very critical, because if you have a machine learning model trained on a known database of molecules and you want to find something completely new, maybe your machine learning model will never be able to give you an accurate prediction of something that is completely different from the database it has already seen. This is why monitoring the uncertainty of your machine learning models and controlling it while it tries to go to better molecules is an interesting part of inverse molecular design. All of this, by the way, was done using the Navica GA package, which is a package that I have built to do exactly this task for different applications in the past. Which I think is also interesting in the sense that sometimes, indeed, building previous tools such as databases or software that allows you to achieve a task is extremely helpful when 1 year later you want to do a more challenging campaign. So this is just some examples of the results. Again, we don't want to go into too much detail, but indeed we see that we find basically we were able to rediscover every family of molecules that had been ever described to go towards single fission, and we were also able to find a number of very, very strange looking, but again, built purely on fragments of synthesized and crystallized molecules, including these sort of sweeter ionic systems, and then we could confirm with quantum mechanical computations that indeed there is something in these sweeter ionic structures that seems to be extremely good for having the correct singlet and triplet excitations for single fission applications. Now, genetic algorithms are nice. We have significant control over the optimization because we can choose to go towards more explorative or more conservative regions. We found indeed a new sort of design principle for building blocks of single fission applications, but as I said before, anything that has fragments is always going to be limited by heuristics. It was us that decided how our new molecules should look by cutting them into cores and substituents. Right? Deciding, okay, we're going to look at all the combinations or combinations between this core and these substituents, but that doesn't mean we, can really explore everything. So the third alternative to look into this task is to go fully data-driven, as I said before. We will train a generative model, purely machine learning, no constraint in that regard. Let's see what this gives us. So what we did is we took form as, again, our starting point. We trained, on one hand, a property prediction model to predict the properties, as before, and then a generative model that is strictly meant to learn the sort of composition and structure of molecules. Okay? So the task of this generative model is just to produce new molecules by sort of interpolating between the molecules of form, which again, we know are good because they are experimentally reported and crystallized. And then we put these things together using a strategy called reinforcement learning, in which first we sort of adapt the molecules that this model gives to make them, neutral and well behaved, and then we keep adapting the molecules that this generative model produces to make them have the correct properties for single fission. And then by doing that, we can obtain a generative model that can only produce molecules that have the properties of interest. You can think about this as trying to take your ChatGPT and then adapting ChatGPT so that it only learns in a language, or it only produces, I don't know, poetry in French, right? So you can indeed adapt these models to make them specifically useful for a single task. So this is basically what we did, just that in our case, our generative model produces molecules, not text. Now, just to show you what it does, if we take the model that has been trained directly on form and we ask it to produce 1,200 molecules, and you look at the properties of those molecules, you will see that the singlet and triplet energies, which are, again, our properties of interest, which are these green and blue curves, are mostly overlapping, because most molecules, the singlet and triplet energy, don't have any sort of particular relationship between them. Now, after the reinforcement learning, we see that the molecules generated by the model have a singlet energy and a triplet energy that are roughly centered in a factor of 2. So indeed, the new molecules produced by the model have roughly twice as much singlet as triplet energy, which is exactly what we wanted. So indeed, the reinforcement learning strategy can be used for this task. And now, we can just generate new molecules. So we ask the model to, invent new molecules for us. And by doing that, we can see that by doing it in different runs, like we ask it one day, then we ask it 5 minutes later, we ask it to produce more molecules, it really tries to cover the chemical space in a way that is not controlled by us. There's no heuristics here. We have not decided what is the way this molecule should look, the fragments it should have, the sort of components it should have, it's completely free to produce these things. And we see that, again, many of the molecules it produces are, such as this anthracene, are molecules that we had already seen, but it's also able to produce molecules that are completely new. And just to give you a very brief example, we managed to categorize them into all of these families, and we were pleased because, again, we rediscovered the known systems and find new ones. And what I found very, very pleasing, and partially why I wanted to talk about this with you, is that the machine learning model was able to find a new family of compounds that had never been reported for singlet fission, which are these sort of coumarines. But this is not coumarin, right? This is an isomer of coumarin. So coumarin is very well known, and isocoumarin, which is one of the isomers, is also very well known. But this is the third isomer of coumarin, which is neocoumarin, and we call it neocoumarin. And we saw that indeed this neocoumarin family, you can do different modifications to it, and it still has these possible singlet fission characteristics. So you can do things such as modify the functional groups. You can go to an amide, you can change it, and it still preserves this sort of proper excited state energies. You can do different modifications to it, and this is really a family of molecules that have this very particular ratio of excited state energies that one can modify. And why I think this is interesting? Well, this is interesting because this molecule was not in the training set. There is not a single example of neocoumarin in the CSD. So this is completely new for the model. But looking at old literature, we found that indeed this molecule had been synthesized by a group by Jones in the University of Leeds in the 70s. So indeed it can be synthesized. It's just that compared to its very well-known coumarin and isocoumarin analogs, it's basically not explored at all. And we also know that it is reasonably stable because it was reported I mean, the complete synthesis is existing. And what we also found is interesting is that indeed it's very sort of impressive that the model could find this molecule because the two closest analogs, which are obviously coumarin and isocoumarin, have absolutely no singlet fission character. So the model was able to find something that is completely new. It was not in training data, reasonable enough that it had already been synthesized and was known to be stable, and also, shockingly, whereas the closest or the most similar molecules you could imagine to this one are known to not have singlet fission properties. So what I mean to say by this is that, of course, we could only do this because we had done a lot of previous work. We had worked on data. We had, I mean, of course, all the data we were used banked on hundreds of hours of people depositing their structures in the CSD, curating the structures. So a lot of work was required to arrive to this point. But there is indeed a world in which fully machine learning driven pipelines are able to find completely new molecules that are still reasonable, that satisfy extremely niche properties of interest. And this is what, in many ways, I think, could also be transferred to challenging applications in catalysis, in transition metal complex design, etc., etc., etc. Now, we do validate the results using quantum chemical data. We have still not validated the results experimentally. So, of course, there is a lot of work still to be done. There is a lot of things that machine learning still has to prove to truly be able to guide, inverse molecular design. But I think future work in these directions is extremely interesting. Because indeed, I think the results so far suggest that these strategies have real merit to them. Okay. So just as an overview and just to wrap up, regarding inverse molecular design, I hope to have shown that over the last few years, since machine learning was implemented in the chemical sciences, advances have taken place quickly. In the beginning, everything was just screening using machine learning. We can now screen. Then more and more people started doing sort of fragment-based approaches using machine learning. And more recently, people are starting to do fully data-driven generative models for inverse molecular design. Of course, as you go to the right, you can increase the creativity of your models and you can truly try and find completely new molecules, while at the same time, you also lose control and you have to keep track of what are the molecules my model is producing to make sure it's not hallucinations, same as you can maybe find in ChatGPT when you ask it to ask a random question, and it can also produce a completely random result. So a lot of work is still required, but the potential for these kind of things, which sounded like science fiction when I started my postdoc 5 years ago is truly, truly, truly coming to me. With that, and without boring you too much, I will acknowledge again all the team that has been taking part on the work here, and you all for your attention, and I will happily answer any questions you may have about this topic. And again, thank you for the opportunity to be here.
Well, thank you, Ruben, for this wonderful talk. I must say that now I understand, but not very much what is that, and also these data-driven things. So now the work is open for discussion.
Let's see if I understand the basics. You need a database which provides the molecular diversity, and you break down the molecules in fragments. You combine them to increase astronomically the number of molecules you can generate. And then you have to train your machine learning system with the properties of all these molecules. But the molecules that you have combined with joining fragments, you don't have any information about them. How do you get the information to train your system with that?
So if I go to the way, let's say the most exciting way, which is the full-on generative one, there are two machine learning models here, right? You have one machine learning model that is trained to predict the properties, and there is one machine learning model that is trained to generate new molecules. They don't have to be trained on the same data, right? So I can have a model that is trained to generate new molecules trained on the CSV, which is massive, and I can have a property prediction model that is trained on 50 or 60 points, because you've done 50, 60 experiments over the last 2 years, and that's 50, 60 experiments on the same reaction is already a lot. And they don't have to be the same, right? The generative model still has seen the entire CSV. So it can propose molecules by interpolating across the entirety of the chemical space, while the property prediction model, maybe it's good within a very, very, very small range, because it has only seen rhodium cyclopentadienyl catalysts. But that doesn't mean that we cannot try and make predictions to the generative model. What is important is, if we can build these models, such as in the case I showed before, in a way that they can try and give us an estimate of the uncertainty of the prediction, and then we can decide how risky we want to be. So we can say, okay, I would like only to find, or only you to be driven by predictions that you are very confident about. Then maybe we will not really be able to find anything interesting, because since the model that predicts the properties has only seen rhodium cyclopentadienyl, the only things that we can possibly find are probably slightly small modifications on rhodium cyclopentadienyl ligand. Now, if we are more, adventurous, we can try and tolerate more uncertainty, and then we can let the model propose things that it thinks have great potential. So maybe it will give us some molecule that doesn't make any sense, because it will try to give us a molecule that will have weird chemistries, maybe something we don't want to do in the lab because it just doesn't make sense. But it's us that can control how much uncertainty in the predictions we are willing to tolerate. And now there's a third alternative too, which is to say, well, give me things that are very adventurous, and then if I care about those, and if I make them, if I decide to make them, and I decide to test them in the lab, I will take this new data that I have obtained by doing this experiment, and I will improve my property prediction model. And I can keep doing this iteratively, right? So the fact that I start with a property prediction model that is trained on small data, of course, it's a limitation. In the ideal world, we have databases of thousands of experiments but we understand that we don't have to have that. But that doesn't mean that we cannot try to do this pipeline, and that also, of course, means that we can refine it iteratively. So I think that is the powerful approach here. And here we are lucky because we have all this database that has a lot of molecules, and because computations are relatively cheap, so we could do the computations on all of these molecules, and then use them for both the property prediction part and the generative model, but it doesn't have to be there.
And just another question, and but this, I think this approach, I can imagine quite well that you can apply, for instance,
I
to
think that it's
you can. No? Okay. You can apply this model to relatively simple properties, for instance, the luminescence or physical properties or whatever. But imagine you want to find a good catalyst for a certain reaction, and then you have many uncertainties that comes. First, how the catalyst works, because you might have several competing mechanisms that can shift very easily depending on the conditions. And second, and more problematic, how the activity is reported in the literature, because you know that the problem of reproducibility is becoming an issue right now, and also it is very hard to convey how strict are you being in administering the activity. You can say my catalyst is great, and then you go to the lab and it's not so great. And I guess that you have to have a very good way to assemble all these sources of uncertainty.
So there are two things that I think are relevant in this one. One thing is that before, models were really data hungry, let's say, but I think by now it's more understood that there are different types of models, right? For instance, when we use ChatGPT, that particular architecture of transformer, and it's known that model architecture works well with language, so we use that for that. Nowadays, I think there is more work in trying to understand what are the specific architectures for the tasks and the data quantities at hand. So if you want to work with a very small number of data points because you are doing things manually in your lab and you just have your own experiments that in principle are reproducible because maybe they were done by you on the same lab with more or less some reproducibility, you can still try to fit models to that. It's just you need to carefully choose what kind of models you would use for that amount of data for that particular task. Right? So not everything works for everything, but we are getting better at knowing what kind of works for what kind of thing. Now the second thing is that at the same time, the amount of large databases even in catalysis is also increasing a lot because we have HTE platforms. Not so many, but if there are a few HTE platforms and they put out a few large HTE catalyst databases, so maybe the reaction you care about is an oxidation, a particular oxidation, say, whatever. So maybe there is no database for exactly the kind of reaction that you're doing, the type of catalyst and the type of substrate that you want to, and the type of conditions you want to look at. But if there are some other large databases, maybe not so related, but that cover a large part of chemical space because some laboratory did a lot of, hydrogenations with a lot of different catalysts, that doesn't mean that there is no information in that database that can maybe be taken advantage of for your particular problematic. Because maybe knowing which catalyst works well for hydrogenation gives you some information of whether this catalyst would work well for the particular oxidation you want to do. Because chemistry is related, right? So the point is that there is HTE, and that even if we don't do HTE, everyone benefits from these large databases being publicly available, on one hand. And the second point is that there are indeed models that are specifically, reasonable and adequate for small data regimes. And therefore, you don't necessarily have to always deal with putting all of these data sets from different people in different papers and harmonize them into the same database. But that doesn't mean that you cannot use them as a pre-training. So sometimes what you do is you pre-feed a machine learning model to some data, and then from there, which is better than random, then from there you feed it again to your own small amount of data, or things like that. So you don't have to put it in the same level, but you can still use it a little bit at least.
Let's move to the next one, Joao.
Thank you. I wanted to ask what kind of format did you use to feed your models? Like from the you took molecules from the CSD, right? So the models, how do you feed them to encode the molecule? You use SMILES, INKI, SDF, or
Anything you can imagine.
okay.
So typically, since we have the cell-to-mole architecture, we can do whatever we want because we can identify all these molecules fully flexibly, and then we can encode them in every possible way that we want. We can build the SMILES, we can build the graphs, we can build the, have the 3D structure that is the minima or the conformational minima that corresponds to this particular. And then you can take all of these sources and you can feed all of those to the same model or to several models, and then you can ensemble all of those models, and even though some models will be better at some things, typically ensembling models with different representations and architectures is good, because then that gives you very good uncertainties.
Okay.
Does it make sense? So what I mean is that, so there are many ways to write a molecule down, right? If I have this molecule, I can try to, this molecule is a Kendro drawing that we understand because we know it represents a molecule, but the computer is stupid, and the computer doesn't know how to see this image and figure out, okay, this is a molecule. So what he was asking is, how do we actually feed it to the molecule, to the model? So what I'm saying is that you can write the SMILES, for instance, and if you write the SMILES, then you can use text-based models, such as transformers, that are the ones that we use for ChatGPT, and we can try and make a model using a transformer architecture. But I can also take this and build a graph, because it is kind of a graph, right? You can write the nodes and the edges, and this is something that the computer can work on, and then I can feed a graph-based model, like a graph neural network, and use that. And what I'm saying is that typically, if you can have many different ways of representing your molecule, you should try all of them, and then you can ensemble them. And if some model that is based on SMILES is bad at some aspects, and some model that is based on graphs is bad at other aspects, maybe just by having an ensemble, you can have an uncertainty in the sense that if something is very clear to the model, every single of these models with different architectures should agree on the predictions.
Okay.
And if something is not very clear to the models, you will get very big discrepancy depending,
Okay. And so the model you are using there is XGBoost, right? And so I know this one is very popular. You were looking for this one straight to the point, or it was, or you compared different kind of models for doing this task?
Everything. Actually, here we use a transformer as well.
Okay. Yeah, thank you.
This one was with everything, and then we also did a graph neural network at the same time for the next paper. We tried everything. And you can have, again, my experience is you can have as many as you. Anyway, this is very easy because it's a single molecule. Now, if I want to predict the EE of a reaction, and I don't mean of a catalyst, now how do I encode a whole reaction?
Yeah.
Doing the conditions. That is the interesting one. A single molecule. This is easy.
Thank you.
In the end, is this okay? Yeah. Okay. So in the end, you need that data to do big data analysis, and the quality of that data, I guess, is very important. You've shown that you calculated, if I'm not wrong, you calculated some of your properties using a particular model, TD, DFT, and a particular functional. How important is that model towards the potential bias of the result? Is there a bias because you use a model or another? Do you work on that? Do you try to see the influence of a particular model on the results of the end results of your data analysis?
So yeah, it's critical, of course. Right? So if your data is bad, then your results will be as bad as your initial data is. Now, the good thing is that, as I was kind of saying before, so not every model, but most models, for instance, every neural network-based model. So basically, when you train a neural network, you start from a random set of weights, right? And what you do is essentially feed these weights to minimize the divergence between the prediction and the observed training set data, right? So if I have, say for instance, to be realistic, we do a catalytic reaction, right? Maybe more representative, and I the student that is doing the results, the PhD student, he doesn't want to waste many hours, so he just looks at the peaks of the spectrum and decides, okay, this one not worth continuing because I have no product or I have very little product that I don't want to do, and maybe the one in which the peak of the spectra is already very good and everything is very clean. This one I will do a column to purify it, and then I will, go ahead with it, which is always, much more time compared to just looking at the spectra quickly and deciding, okay, this one out. So you can fit models to preliminary data or data that is low quality, and then once that model is fit, you can continue fitting it to a smaller amount of higher quality data, and that's always or typically much better than fitting it from zero, which means that you need less data of the high quality type. So this is a simplification, but there are many multi-fidelity architectures that let you do this kind of stuff. Therefore, even though in this case, indeed, we are using a very small, we are using TDDFT data, which is not the truth or the absolute truth for the, I went in the opposite direction. We are using TDDFT data, which is not the absolute truth to make our molecules, and maybe indeed, then this goes to, then we our experimental colleagues make this molecule, and the molecule turns out it's not correct because the TDDFT was wrong in the first place, which I don't think it is, because when we first look at this, at this problem, we checked against experimental observations, and we saw that the TDDFT in this particular case correctly identifies molecules that are experimentally known to have this property. So we were kind of confident that the TDDFT is pretty decent. But if it happened, then we could still take a selected number of experimental results and try to refit our models to adapt them to this data and continue from there. So as long as you know what you can expect from the quality of data you put in, and you are coherent with that, I think you're fine.
Question?
Yeah, you are using some terms that for me require some precision. When you say small amount of data, how many data do you mean? Because quality of the data, as you say, is a point for catalysts, but if you think about biological activity, whatever, reproducibility is still that's another issue. So, how many data do you need to start with?
So, let's say, depends on how much accuracy do you need in the first shot. You know what I mean?
Yeah, no, but I think essentially you need to generate your own data to be sure that your data have, well, at least homogeneity in terms of quality. And of course you have to generate your own data. That means that 50, 100 data are already a lot. So that's enough to start with, or not? You need to go to 1,000 data? Or
No, let's start with that. But again, if you start with little data, and especially how, let's say, there are many small issues to discuss in this aspect. So I'll give you an example. You start doing some experiment with biological activity. So you have a small compound, and you know that you're exploring small modifications to it because you have already a synthetic protocol, so you can try to put different substituents in the R2 position of the molecule. Okay? And then, so you have these 10 data points or 50 or maybe 100, but they are all very similar, for instance, because essentially everything is the same except for the R2 position. Okay? And then we try to make predictions, or we want to make predictions on something very different from the original scaffold. It's going to struggle, right? Because, it's not only the quantity of data, it's also how diverse is the data. Is the data covering, so now if you take a small database of points, but to cover a lot of space, because you try 10 different scaffolds, okay? Maybe the model will not be super accurate to the small substituent modifications, but maybe it can tell you these two scaffolds look more promising than the other, things around making this modification. And even though it's maybe not quantitative, maybe that's enough to guide you or to help you decide what are the next experiments to do. So there is a lot of nuance to this. This is what I need to say. It doesn't have to be thousands, for sure. It depends on how much, what do you really want from the model, how the original data was designed, and how willing are you to keep refining.
Thank you. I think a lot of opportunity. Let's see.
Thanks, Rubén. Could you guide us a little bit about how do you monitor uncertainty? Say, for example, with neokumarin. This has never been applied to single fission.
So, well, in the case of neokumarin, the predictions seem to be quite accurate. I mean, the models don't have very high uncertainty for the predictions that they. Now, the uncertainty of the machine learning models is also not perfect. Like the model cannot know 100% whether the uncertainty puts in a prediction is accurate or not, right? We have to deal with that. What basically the uncertainty means is that the model believes that the neokumarin structure is well represented or well represented enough in the training data it has seen, so that it is confident that it can make a prediction that is represented. And indeed, when we did the EPFL results, which is the end of our limits for now, we confirmed that the model prediction agrees with the EPFL results. Now, how to build and how to test, I think I have an extra slide on this actually. You can, when you train your models, you can check whether the uncertainty is what we call calibrated or not, right? So what you do is, you plot this kind of curves, right? You plot this kind of curves in which you change the validation data, you check, I mean, basically, before you use the uncertainty of a model, you can check whether the uncertainty of the model actually is, kind of appropriate or not. So you typically see in papers this kind of plots for calibration of the uncertainty. And I mean, this one is a bit more simple. You just see that we color the points based on the uncertainty, and the points that have small uncertainty have small error, and the points that have high uncertainty have much bigger error. So indeed, we know in this particular case, again, which is a very easy case, it's a simple property that we can compute with the DFT and so on, that the models have pretty decent uncertainties. But indeed, this is something you have to also take care of when you are fitting your models.
Thanks.
Yeah, thank you very much, Rubén. This is great. This is a whole playground of synthetic chemists with a lot of backgrounds. So I guess there will be so many things we can all do together once you start here, or I hope so. But so one curiosity, silly question. You've been going from machine learning to genetic algorithm, and then at the last, the fully generative models. But in my experience, the best chemistry we have developed is the one we were not looking for. So here we are kind of optimizing a parameter for a given reaction or for a physical process like the singlet triplet. So we're that step from going to whatever would be the best for this to go for, give me something that I even didn't think about it. Is that a possible future or not? What do you think?
That maybe machine learning is not for everything. Maybe chemists still have a job
Yeah,
to do.
then this is nice.
This is what I would tell you.
That's what you say, right? For us to be happy.
I believe so. Now, things that are interesting. Sometimes you, for instance, again, I didn't go into too much detail, right? But so we find neokumarin, right? And neokumarin, we did modifications to it, and we see that you can modify the second fuse ring, you can modify the capping terminal group, the lactone type couple you can change this at P to ends, but you cannot change the position of the lactone, of course. You cannot add or remove fuse rings, and then we studied it. Why is this molecule have these particular energies? And we can also check the model, because the model can also give us why it believes this molecule to have these particular properties. And then based on that, we observed that indeed, actually, I think I have a slide for this actually. It's just cool, right? So we see that, these are coumarin and the other one, and the singlet and the triplet are not a factor of 2, so they are not good, right? And then we have benzofurin, and benzofurin does, and this is known. Benzofurin has been studied for singlet fission by previous experimental groups. So then we realized that what the model found is basically an alternative to benzofurin, in which you cap the molecule with the lactone instead of with just the oxygen here. And it turns out that what is really good for the singlet fission is to have these weird two sort of cis double bonds that are isolated there and cannot conjugate too much. And this is interesting because this is a design principle which now we can exploit and we can think about new things about, And indeed, if I tell you this and I tell you people in organic electronics are going crazy because they have the design principle of trying to find two, cis double bonds that are not two resonating with one another. Now we can. So it doesn't have to be one or the other. I think we can work with the machines, not against them.
Question?
Sorry, I have another. You said that you can ask the model why or how is it seen, a property is good somewhere, but the model is a lot of data. How do you see this particular molecule is going to be good at this because?
So in this particular case, I think I just don't have a slide for it. I'm gonna check quickly. I have some catalysis just in case. In case people were booing me. So in this particular model, we had the transformer included. So the transformer, we have a graph transformer, and graph transformers have the very nice property that they are based on attention. So you can actually plot the attention of the graph transformer, and it basically, in this case, since we are predicting excited state properties, it basically gives you the transition orbitals, and it's very nice because you can clearly see that it believes. It tells you where it thinks the singlet is being formed and where it thinks the triplet is being formed. And in this particular case, it's very illuminative because it basically tells you, I believe that in this molecule the singlet is going to be here, and then I believe that when the triplet happens, it's going to be here. And we can confirm our design principle based on this. And I'm not going to say everything, but most machine learning models today can be made increasingly explainable depending on your choice of representation and property. But it doesn't have to be black box.
And for the future, do you think you can integrate like LLMs with that, so you can really ask your model, hey, why do you think this? Like for non-experts, that you can interact with your, like non-experts could really interact with your model and.
Well, with agents you can already do this. It's just that it's maybe not something that is generally available to the public, but you can already ask agents these kind of questions, and the agent will call the machine learning model, make the prediction, look at the results.
I'll tell you. Awesome.
I've worked with a startup, but they do this.
Oh, awesome, thanks.
Okay, another question. Well, if not, I have only 20 questions. No, all the questions I had that you have already talked about. And the first one is the importance of this data in this kind of approximation. And one of the excitement when this data-driven approximation was is the discovery of new drugs. Well, and there have been something positive in this field, but however, they quickly find that the data which was in the literature were mainly garbage.
Yes.
So now the direction is how to create adequate data. So that means that chemists, we are, even if you are, we work as technician for the machine, but we have to create good data, no? So I don't know if you agree with that.
I think in this particular case, what happens is that data, as Juan was saying before also, data as collections of data from many people over many institutions in many different settings is super dangerous. Because the same, we know this, it's not surprising. It's very linked to reproducibility concerns in general. So I think, as long as we think that the important thing is not to be naive and realize, look at the data, be familiar with the data, you know what the data is looking at. I think if I ask any chemist in the room that works in a given area to check 20 papers and tell me, how the data looks to them, look at the spectra, look at the quality of the papers, they would be able to tell me maybe pretty confidently, I believe, this data I would believe more than this data, for instance, right? But the machine is dumb, the machine doesn't know this. So the machine, if you take, I make a bot that scrapes tables of yields on the supporting information of every publication in the last 20 years, and then I put everything together, that's going to be a mess for sure. So humans are still very much needed in the loop.
And the next question is about Jesus. With this, you put this creativity. It's a great word. Who is the creative? Is is the chemistry of the machine. And next, once I heard a lecture from David Macmillan, the Nobel Prize in Organochemistry, and he had this approximation named serendipity at work. So he was putting reaction who didn't work. I mean, he just mixed substance who cannot make any reaction within them. And to look at new reaction or new way to do chemistry. Can we take these way around, not taking all the what is working, but what is not working to create new way?
So one of, I mean, it's also very linked to the data quality. Let's put it this way. Thinking about data quality, I take data from every paper that has been published in organometallics this year, and I take all their tables on a particular reaction, and I put it together and I try to fit a model. Typically, if you look at, I mean, you can examine where is the model wrong, because I can, you know, I give the model 50% of the data, and then I look at the other 50 and I check did the model make the correct prediction or not. This is, of course, something you have to do to check the quality of your model. It's also very, very good at finding problems with the data, because, you know, if indeed the model makes a prediction and then you look, okay, the model made this prediction because of this and this and that. However, the experimental result was this. Very often in my experience, this is a way to detect also problems that were in the data originally. So my point here is that same as serendipity, and I mean, which you do a lot of experiments and many of them don't work, and then you have a large amount of data to process. Machine learning not only has to be something that you use to predict, it's also very useful at curating, polishing, identifying mistakes, identifying missing pieces in data that is existing. In fact, in the CSD, so when we mine the CSD, right, everyone that, I mean, I guess anyone that has worked here probably knows, but the CSD goes back a few number of years. So if you start mining things from the CSD, eventually you will find some article, some crystal that was deposited by some institution in the Soviet Union back in the day. And I mean, it's not saying that they didn't do good science. Of course, they were doing pretty good science, but machines and X-ray technology and diffraction and the software has also improved over the years. So very often you find wrong assignments. You find missing hydrogens, of course, because they didn't have the resolution. You find that some amine and some carbon have been switched in the molecule. And these things are very, very hard to identify by hand. Like, nobody would want to look at thousands of CSV entries and try to identify mistakes. This is a pain in the ass. But the machine, who is, you know, works for free, you don't have to pay it too much, a bit of electricity, it can look at millions and millions and millions of points, and it, you know, by trying to make good predictions, it also lets you identify possible errors. And in my experience, so we did this for oxidation states, right? The oxidation state part here, we took the data, and then we train models to predict spin states and oxidation states. And then we can look at oxidation states, and we compare against the label that the, whatever, you know, typically the PhD student, when they made the deposit in the CSD, have to typically put the name of the compound, and you will put, you know, oxo, iron, 5, whatever, and then we took those labels and we compared, okay, what is the machine learning model giving, what was given in the CSD entry. And then in many of these cases, we went to the paper, and in the paper it was different than in the CSD entry. So the model was right. But whoever wrote the entry in the CSD, maybe because they were depositing 20 entries that day, and they were copy-pasting the name, and they forgot to change the 5 to a 4. So my point is, you know, it's also something that machine learning is good at, identifying problems with data and analyzing large amounts of, you know, things like serendipity experiments in which the, you know, you want to find the outliers. This is also something you can do.
Okay, we're gonna finish here. Thank you, Rubén, for this exciting.
¿Está bien? ¿Entretenido?